Back friends, in the previous video we discussed about the molecular geometry and facts all about the shapes of molecules, and in this video we are going to discuss about the valence shell electron pair repulsion theory. So the valence shell electron pair repulsion theory is helpful in understanding the modification which are observed in the shapes of molecule as the result of the presence of lone pair. So as we discussed previously, that we have the molecular geometry and then we have the valence shell electron geometry. So we may have the valence shell electron geometry, that is the arrangement of the valence shell around the central atom, and we sometimes we may have lone pair. Kwa hiyo uwepo wa lone pair unasababisha valence shell electron geometry zibadilike kwenda kwenye molecule. Kwa sababu gani? Ukiremove lone pair ndio inabakia geometry ya molecule yako. Kwa hii theory inakusaidia katika wewe kumodify. It gives quantitative explanation on the bond angle observed in a covalent molecule and some ions. The valence shell electron pair repulsion theory was formulated by scientists Sedgwick and Powell, and hence the theory is always known as Sedgwick-Powell theory. So here we have the assumptions of the valence shell electron pair repulsion theory. The first assumption said that bonding orbital tend to remain as widely separated from one another as possible, so as to minimize repulsion between them. As we know that the electrons, they are negatively charged, and as we know from the fundamental law of electrostatics, that the like charge they tend to repel. So electrons zote negative charge because zitakuwa na repel, zitakuwa na sukumana. That is the first assumption. The second assumption, lone pair orbitals exert greater repulsion than bonding pair orbitals. Lone pair zinaongeza repulsion kuliko bonding orbitals. Now third assumption, repulsion is increased by increase in electronegativity of the central atom. So electronegativity ni uwezo wa atom fulani kuvuta electron, to pull electron towards itself. The ability of an atom to pull the electron towards itself increases, then the repulsion of the electrons increases. So even the bond angle will decrease. Why? Because bond angle will decrease with electronegativity increase. So according to valence shell theory, repulsion between electron pair is according to the following order: lone pair vs lone pair repulsion is greater than lone pair vs bonding pair electron, and this is greater compared to bonding pair repulsion. So in the sum of the atom you will have two lone pairs. The repulsion between two lone pair will be greater as compared to the repulsion between lone pair and bonding pair. And if you don't have lone pair at all, means the repulsion between bonding pair is very small as compared to the repulsion of other pairs of electron. So the electron pairs will tend to arrange themselves around the central atom in such a way that there is fewer lone pair interaction possible. Kwa electrons zitajipanga kiasi kwamba the lone pair interaction ambayo inatokea inakuwa ni ndogo sana. So valence shell electron pair repulsion theory explains the arrangement of all electron pairs around the central atom, and hence the term valence shell electron pair repulsion shape for electron pair geometry. Kwa hiyo kutoka hapo tunasema kwamba electron domains, these are areas of how high electron density, such as bond and lone pair of electrons. Kwa hiyo electron domain ni maeneo ambayo yanakuwa na electron density kubwa. Note that the valence shell electron pair repulsion theory does not give quantitative explanation on bond angle. Kwa haiwezi katupa size ya bond angle kabisa ni 120. It cannot be used to predict the size of bond angle. It can only be used to explain observations made on the size of bond angle, that is, to reason behind those sizes. kwamba hii inaweza kutusaidia kusema kwamba bond angle imepungua au imeongezeka. Kwa nini iongezeke? Presence ya lone pair inapunguza bond angle. Absence ya lone pair ina increase bond angle. However, you may use the following rough estimation that every single lone pair decreases the bond angle by 2.5 degree from the expected bond angle in absence of lone pair. Kwa hiyo hii ni expectation ambayo ni sio official, kwamba lone pair moja na decrease bond angle kwenye 2.5 ukitoka kwenye expected bond angle ambayo itakiwa. Kwa hiyo tutaenda kuona ni kwa jinsi gani ambavyo hii rough expectation inaweza kutumika au mazingira gani haiwezi ikatumika. Kwa hiyo kama unavyoona hapo kwamba ile assumption sio nyakati zote wanakuwa sahihi. But this is not always true. It may be just useful in memorization of some bond angles. The rule hold more in absence of pi bond. Kwamba hii rule inakuwa ya ukweli kama pi bond inakuwa haipo. In presence of pi bond, the decrease in bond angle due to stronger repulsion of lone pair becomes smaller because pi bond exerts stronger repulsion. Kwa tukiwa tuna pi bond, decrease ya bond angle inakuwa ndogo kwa sababu ya repulsion kuwa kubwa. So in absence of lone pair, bond angle of various geometrical shape is as follows. Kwa ukisikia linear molecule bond angle yake inakuwa ni 180. Hapo kama hatuna lone pair. Tetrahedral inakuwa ni 109. Trigonal planar 120, 109.5. Octahedral ni 90 na trigonal bipyramidal ni 120 au 90, 120 na 90. Kwa hiyo kama tuko na lone pair, hizi bond angle zinaweza decrease by 2.5 au etc. So here let's see some of the shapes of molecules and ions. So let A to be the central metal atom and B to be the bonded electron pair, and E for unbonded electron pair that are lone pair. So we are categorizing these molecule on the basis of type of hybridization, and we are starting with the Sp hybridized orbital. Now to start with Sp hybridized orbital, we know that the Sp hybridized orbital their shape is linear. So the bond angle is required to be 180 degree. But sometimes, for example, if you are taking AB2, means here we have no lone pair. For example, here we have beryllium chloride. So for this molecule, it will be beryllium, then chlorine, and our bond angle will be 180. The shape will be linear. No any modification can take place in this molecule because we don't have lone pair. So kwenye other molecule ambazo ziko kwenye kundi hilo unaweza kukuta kama beryllium fluoride, alafu kuna hizi hapa beryllium hiyo hapo hydride, kuna zinc chloride na mercury chloride. Lakini sometimes you may have A, B, means you have one bonded atom and then you have the lone pair. So meaning that, for example, here you may have a certain atom A which is the central atom, and then maybe you have lone pair here, and then here maybe you have the bonded atom B. So in this case the lone pair can be removed here and will not affect anything here. So what will happen is that our example here is carbon monoxide molecule, and in the carbon monoxide we will have one oxygen, and then we will have a lone pair. So having lone pair here, when you remove the lone pair, elimination of the lone pair, you will get the structure of carbon monoxide to be like this, and the lone pair can be put here in. So the presence of lone pair here does not affect anything. Does not affect anything in this molecule. But now let's see on other molecules of sp2 and other types of hybridization. So for sp2 hybridization, we are again using the same letters. So if you have A, B, 2 and sp3, I mean sp3, for example here sp3, for example, is beryllium boron chloride or is boron fluoride? Boron fluoride. So if you have this and if you have no lone pair, the shape of the molecule is trigonal planar. The shape of the molecule is trigonal planar. Sp2 hybridized orbital, they are trigonal planar. So trigonal planar molecule will appear as boron, and this is not the beryllium, it is boron. So will appear as boron, and then will appear as chlorine, then chlorine, then chlorine. So this will be the appearance of our molecule, trigonal planar. But for the case that we have lone pair, for example, if you have the A, B, 2 and then one lone pair. So our example here is sulfur dioxide. Sulfur dioxide. And in sulfur dioxide, we have sulfur, and then we have oxygen. We have oxygen, and then we have lone pair here. So here, this lone pair, if we remove elimination of the lone pair, will remain with the structure. This one is removed and this line will be cancelled. So the structure remaining will be like this, and the lone pair will be here. So it will be bent. It will be bent in structure. And do not confuse, kwa sababu kule mwanzoni nilikwambia group 6 element lazima ziwe zina two lone pair. Lakini hapa usio confuse kwa sababu gani one of the lone pair imetumika kwenye bond formation. Kwa sababu ili tupate number of lone pair inakuwa ni sawa na number of valence electrons minus number of bonded electrons divided by 2. This will be the number of lone pair. Kwa mfano hapo kwenye sulfur yenyewe ni group 6 element. So number of valence electron itakuwa ni 6. Number of bonded electrons kwa hapa kwenye sulfur maana yake inaonyesha kabisa ni 4. Kwa sababu gani? Hapa imeshao ni bond 1 bond. Kwa ni 4. Tukidivide by 2 tutapata 2 divided by 2 which is equal to 1. Kwa kwenye mazingira mengine, kwa mfano ukichukua oxygen ukaweka hydrogen, oxygen itakuwa na 2 lone pair. Kwa sababu gani? Number of valence electron ni 6. Tukiminus number of bonded electrons hapo ni 2 divided by 2 utapata 4 divided by 2 which is equal to 2. So hapa number of lone pair ni 1 hata kama ni group 6 element. Kwa hiyo utakuta kwamba the structure ya huyu hapa inabadilika, inakuwa bent. Na ikishakuwa bent, basi mwisho wa siku unajikuta kwamba geometrical shape ya molecule yako imebadilika. Lakini we have something to note hapa. Bond angle in sulfur dioxide is 119 degree and not 117 as one could expect, because the pi bond in sulfur dioxide structure exerts strong repulsion. So stronger than sigma bond but slightly less than lone pair. And therefore, there are some degree of avoiding pi bond repulsion as it avoids pi bond lone pair repulsion. And hence the bond angle becomes close to the ideal, which is 120 expected bond angle in absence of lone pair. Kwa kama tungekuwa hatuna lone pair hapo, bond angle ingekuwa 120. Lakini imekuwa 119 kwa sababu gani? Presence ya one lone pair ingeitoa kutoka 20 kwenda kwenye 117. Sababu tulisema one lone pair na decrease bond angle by 2.5 degree. Kwa kutoka 120 ingeenda kwenye 117.5. Lakini presence ya pi bond pia increase repulsion between bonds. Imeongeza hii angle mpaka kufika kwenye 119 ambapo panaonekana kama vile hapana lone pair kabisa. Kwa hiyo from there let's go to see on sp3 hybridized orbital. and how are they changed in the presence of lone pair. Kwa hiyo kwa mfano hapa in sp3 maana tunaweza kuwa tuna sp3 hapa, maana tutakuwa tuna 4 bonds. Hapa tunaweza kuwa tuna ab4 mifano ni hiyo methane. Kwa hapo hii hapa by shape in the absence of lone pair utaikuta iko tetrahedral ambayo ina exist as carbon, then hydrogen. So tetrahedral appears like this. This is tetrahedral. So for the case this has no lone pair and the shape will remain tetrahedral. But if we have one lone pair, saying we have one lone pair, it will be AB3 then. So for example, here is our ammonia, and in ammonia we have nitrogen, then we may have a lone pair, then we have hydrogen, and we have hydrogen. So if we elimination of lone pair, if we eliminate, you will see that the tetrahedral changes into pyramid or distorted tetrahedral. So here the molecule shape is trigonal pyramidal, or sometimes is simply called pyramid or distorted tetrahedral, with bond angle about 107. So 107 comes from 109 minus 2.5. That is 2.5 is due to the presence of lone pair. So the shape of the molecule becomes nitrogen and then hydrogen, and can be called as pyramidal or trigonal pyramidal. So if we have two lone pairs, A, B2, E2, for example, in water, if we have oxygen, then you have hydrogen, and then you have hydrogen, then you have lone pair, and then you have lone pair. So the shape of the molecule will be like this. Removing two lone pair, the shape will change to bent. And the water molecule will appear like this. So what we can say here is that in this case the shape is bent with bond angle. Bond angle here in water is 104.5. Why this? Because the original bond angle was 109.5. Kwa hapo una minus 5 kwa sababu gani? Tuna two lone pair. Now every lone pair in a decrease 2.5. 2 times 2.5 will be equal to 5. Minus 5 here utapata 104.5. And then from there, let's move to the Sp3 then D hybridized orbital. Sp3 D hybridized orbital. In Sp3 D hybridization, the absence of lone pair in this will lead to the shape which is trigonal bipyramidal. So if we have AB5, for example, is phosphorus pentachloride, this is trigonal bipyramidal. We may draw it as phosphorus, and then bipyramidal means we have a triangle here. We have a triangle with chlorine, and then chlorine, and then from there we have this structure. We have this structure from there. So yeah, it appears something like this. It's called trigonal bipyramidal. So this is the shape if we have no lone pairs. Now assume we have one lone pair, for example AB4 For example, in sulfur tetrafluoride, now the shape will change. The shape will change, as you can observe in the subsequent diagram here. That here we had one lone pair. We have one lone pair here, and this lone pair, if it is removed, the shape changes. Elimination of lone pair changes the shape into this was trigonal pyramidal, and this is trigonal pyramidal. And if you have two lone pair, the shape changes into scape or T-shape. So as you can see, the presence of two lone pair, the molecule changes into T-shape. And the example is iodine. Presence of three lone pair, the molecule changes into linear. So this is how the hybridization takes place. And our last molecule, our last type of hybridization is Sp3d2 hybridization. In the absence of lone pair, this appears as octahedral in the absence of lone pair. And in the presence of single lone pair, molecular shape changes into square pyramid. And in the presence of two lone pair, it changes into square planar. So the shape changes into square planar. As you can see here, presence of two lone pair changes into square planar. And here in this table we have summary of some of the compounding possible shape of species containing atoms of representative element. So number of electron pair, number of bonded atom, number of lone pair. So you can see some of the shapes here, and this summarization I got it from Chandi book, so you may find it in Chandi. This is just the summary, and it continues even in this page. Is just the summary of the atoms shapes if we have lone pair, and some of the example molecule in this column. So I can't explain them all, but I beg you to visit the Chandi book, and then you will see these shapes. And I hope if we will get time, we shall discuss about some of the questions of this topic, so that we can be in the same phase. Subscribe to the channel and click the link below to join my Telegram group, so as we can discuss different facts about chemical bonding and other aspects of general chemistry and even physical chemistry. After this topic, we shall start with the physical chemistry, and I hope I will start with the end of the topic, whether it's the chemical equilibrium, thermochemistry, or even chemical kinetics. Stay with me, stay tuned, and subscribe to the channel for more updates. Have nice studies. Thank you.